Hello, I'm Matt Eland, or at IntegerMan on Twitter, and this is Stand Back. I'm going to try data science, so thank you all for keeping your distance. I appreciate that. So I love data science, and my hope is that by the end of our talk today, you're going to see what's so exciting about data science and what we can do with it. Right? So I'm hoping that you're going to learn a little bit more about the data and the data professionals in your organization, including the data you already have and the data you might easily be able to collect. I'm hoping that you're going to see how we can use data science and machine learning to take our existing software engineering skills and add a layer on top of that where we can build new things that we couldn't before without machine learning. That's what really gets me energized about data science and machine learning in general. And finally, I hope that you see how adding some knowledge into data science and machine learning and statistics and all these things that are related to it is going to help re-energize your passion for software development and technology, and can help potentially re-energize your career. So I love data science, but I'm actually not paid to do anything at all with data scientists. I am a software engineering instructor here in town at Tech Elevator, along with a few of my graduates and fellow instructors here. We are a great way of getting into tech if you are ever looking to hire, volunteer, mentor, or teach, or help us with maybe DevOps or other things. Talk to me or talk to somebody on staff with a Tech Elevator shirt. We'd love to talk to you about that. But I'm going to assume that you're here to hear more about data science than this, so we'll talk about my hobbies instead. So in the evenings, I love to spend my time making content on data science and machine learning. I wrote a blog, a YouTube channel, and I do talks like this one. You can find my content mostly at mattondatascience.com. We'll redirect you to my YouTube channel. But I like to have a very accessible tone to data science because I think it's so empowering and so exciting. So I love it. And in my copious amounts of spare time when I'm not teaching and I'm not building content, I'm also a master's student here in town at Franklin University where I'm studying data analytics. So that's a lot of fun stuff. It should be clear to you by now that I am not an expert. I am not a data scientist. I am, however, very good at learning data science. And I'm hoping that my journey in learning data science myself is going to help you understand what's out there and how you can get started learning data science and why that might be a great thing for you to do. Okay? So I'm going to be really happy with this talk if you come out of here understanding a little bit more about what you can do with data science and why that matters to you, and who can do data science and what skills they need and what ways of getting into data science there are for you. Okay? So before we go any further, I just want to point out some things. In the upper right corner of every slide, I have a link to matteland.dev/tryds. This is a website I created that has a link to all sorts of resources that we're going to be talking about, as well as the slides for this presentation. I will also embed a YouTube link for a recording of this presentation for you to share with your coworkers and friends if you want to do that as well. In the upper left corner is my Twitter handle. I'd love if you give me a follow there so we can keep talking about data science after the conference. Okay? So machine learning models. I like to think about machine learning as kind of like a calculator, right? We are building a calculator that we can go out and train, right? So let's say I'm an expert in something. I know a lot about something. I know how to predict whether a loan is going to default in a bank, for example. But I can only evaluate so many potential loans in a day. Data science and machine learning models, they can evaluate thousands of them in a single minute or second, right? It helps us build larger and larger and larger systems that can scale well and make predictions based on historical data and observations that they've seen. Also, even if I really know a lot about data science and I know a lot about my loan process at my bank, I might not know all the ins and outs and hidden associations in the data. A machine learning model learns the ins and outs of your training data, and it can find these little hidden associations that you didn't even think of looking for. And so machine learning models can help us do things larger at scale, and they can help us find hidden insights that we weren't even aware to be looking for. So this is why I love data science. It's so much fun. But typically in a supervised learning form of machine learning, we are taking a data set that has historical information as well as some predictions or some facts. And we are training a machine learning model to memorize these pieces of data. And it's going to take a look at this and it's going to say, hey, for example, here's a list of movies as well as whether those movies are Christmas movies or non-Christmas movies. So it's going to memorize, okay, well, this movie came out in July, it starred this person, it had these tags associated with it, and this was not a Christmas movie, and this one was. And your machine learning model is going to start to fit to that data. It's going to understand the relationships there, That's going to say, okay, well, I think I'm understanding what makes a Christmas movie and a non-Christmas movie a non-Christmas movie. So now if I see something new, I can make some predictions about that, about whether or not that should be considered a Christmas movie. This is kind of a silly example. We'll talk about why I did this with my spare time in a bit, but you can think of this in a more realistic context in approving or rejecting a loan, or determining whether or not something is cancerous or benign. Right? So all these things really can help us, but we need some historical data typically with supervised learning. Right? So a machine learning model essentially takes in some features, such as information about your movie. We have our pre-trained model that evaluates those features, and it generates a prediction. So it really is like a calculator, but we have to spend some time building our calculator. So if we think about software development and building a server or a web application, it takes us months potentially to build a new application. And then we deploy it to production, and people can interact with it very quickly. So it took us a long time to build our application and deploy it, but it took us a user a very short amount of time just to log in. The same concept is true with data science. We're spending a lot of time building and training our models, and it can actually take 10 seconds to several days to train your machine learning models to get the accuracy levels that you need on larger data sets. But once we have those models, they're very quick to evaluate new requests. So very similar to what we already work with software engineering in those concepts. Okay? But as you're just starting out in data science, I want you to focus on 3 core tasks that you're going to start with. Those are classification, regression, and clustering. These are kind of the basic elemental tasks of machine learning. And of those 3, I would strongly push you towards classification. We'll talk a little bit more about why that is later at the end today. But these 3 things are the kinds of things that you can do with data science. We'll talk about each one of these in turn. So classification is we are predicting a single categorical label. So we're predicting whether a mole is cancerous or benign, or we're predicting the day of the week that some piece of news is going to come, or something like that. These are all categories that we're predicting, right? There's examples of binary classification where something is either going to be true or false, or multi-class classification where it could be more than 2 different categories, right? So some examples that I've done in the past. This one here is actually my favorite machine learning experiment I've ever done. My lovely wife and I were having a discussion about the movie Die Hard and about whether or not that movie should be considered a Christmas movie. And we had a bit of a disagreement, we will say. But I had been studying machine learning. I said, you know what? Let's train a machine learning model to memorize whether or not a movie is a Christmas movie. And we're going to show it all these movies except for Die Hard. And once we have a model that performs very well, we're going to show it Die Hard and see what it thinks about Die Hard. And my wife and I were able to resolve our disagreement, and yippee-ki-yay, Die Hard is absolutely a Christmas movie. Prove me wrong, right? But that's an example of classification. We're predicting whether or not a movie that it's never seen before is going to be considered a Christmas movie. Now that's ridiculous, but I like ridiculous things. A more serious example would be the loan application process or cancer classification, as we talked about. Now, an example of multi-class classification is where something could be one of many different categories. I like to do hobbyist game development from time to time, and in the game development industry, there's something called the Entertainment Safety Ratings Board, or ESRB. This gives a parental guidance rating for an unreleased video game. So what we can do is we can train a machine learning model based on historical games, the types of content that they've had in them, and the ultimate rating that they got. For example, if I'm trying to release a new game and that game has some alcohol references, maybe some crude humor and some cartoon violence, it's going to look at all the historical games that looked a little bit like that and the ratings that they got. And it's going to say, hey, Matt, there's about a 10% chance that your game might be given an M for mature, maybe a 35% chance it might be given a T for teen, and maybe a 20% chance it might be E for everyone, for example. So it's predicting with some level of confidence what group or class something's going to be in. Okay? So that's multi-class classifications where we have multiple different types of things, not just true, false. Regression is very much like classification, but instead of predicting a single categorical value, we are now predicting a single numerical value. So we might be predicting the sale price of a car, given the amount of distance that it's driven, and the number of accidents that's been given, and things like that. I did one last week before, where I predicted the number of penalties that 2 NHL teams would collect together when they played against each other. So I trained it on historical penalty information. It was saying, hey, given these 2 teams, yeah, we're going to need some pretty good officiating because there's going to be a lot of fights. That's an example of regression. We're looking at features and predicting a numerical value. The very first one that I ever did of these, I wasn't even aware it was a regression experiment at the time, but I am a serious, serious night owl. And any time that I can spend sleeping in the morning, I'm going to take that time and sleep. And so I had to wake up and scrape my car off in the winter. And it varied how much time I'd need to spend scraping off my car. So I built a system to automatically pull weather API information, store it in a database, and then I would manually record the amount of minutes I spent in the morning scraping off my car. And by the end of that winter, I had a system that was able to predict the amount of minutes I'd need to spend scraping off my car in the morning. And so I was able to get an extra 3 minutes of sleep, which only, 3 weeks of work and manual recording things. And of course, by the time the next winter rolled around, my wife and I had a garage and the model was worthless. But it was still a great way of learning machine learning, right? Actually, I have a talk coming out tomorrow for a different conference that's predicting whether the television rating an episode of Doctor Who would get. That's the number that we're trying to predict. Again, I like to do data science and do ridiculous things with it. But it's based on the traits of that episode, who's in that episode, who wrote it, that kind of thing, and historical trends. So trying to save Doctor Who by giving them some machine learning help. I don't think it's going to work, but I got to do my part. So that's regression. Now, regression and classification are what we call supervised learning, where we have to feed it historical information about our data with labels in them, such as whether or not a mole is cancerous or benign, or the amount of money a car sold for. Clustering is unsupervised learning, that we don't need to give it a training data set. Instead, we give it raw data, and it finds associations in that data. For example, if Store Trek, the online store of Star Trek, wanted to open 3 physical stores in the United States, they might use a clustering algorithm to find 3 clusters of people. So if they had all of our information about where we live, which they probably do because they mailed us our shirts, right? But they could build clusters of these things and find, hey, where's the best placement of each individual store inside of the United States? We're trying to minimize the amount of travel time on average that somebody needs to do. So it works really well with geographical information. We're saying, hey, I've got enough for 3 clusters, tell me where to put my stores, or whereabouts to put my stores. But you can also work with non-geographical data here. For example, if I was working with my marketing department and they wanted a list of frequent users, infrequent users, and people who just never log into the system, well, a clustering algorithm might be able to identify them based on their usage characteristics. So you see clustering used a lot for segmenting populations based on different characteristics. So unsupervised learning, like clustering, is going to find associations in your data and group things based on that. Okay? So these are the 3 basic types of machine learning: regression, classification, and clustering. I strongly recommend you start with classification. It's a little bit easier to think about classification than the other 2, but they're all very good ways of getting started. There's a lot more that we can do with machine learning, and near the end of this talk, I'm going to talk to you about some of those things. But I want to talk to you more about some of the people who do machine learning first, and the technologies we use in that process. So the types of roles in data science are typically your data scientist is the one you think of first because it's literally in the name, right? Data scientist. Your data scientists are a kind of a programming role, but their focus isn't mostly on the code. It's on the machine learning models that they're producing. They're taking your data, they're trying to understand the data, prepare it, clean it, get it into a usable state, and then they're trying to build a reliable and non-biased machine learning model. We'll talk about bias in a bit. So data scientists are maybe a bit more of a math-heavy role than the others that I'm talking about here. And we'll talk more about math at the end again. But if you really like training machine learning models, working with data, evaluating these things, finding these relationships, data scientist is a good role to look into for you. Now, if you really like communicating insights from your data, a data analyst might be more your speed. Your data analyst may or may not be a programming role, depending on your organization. Some of them may be using Python code to manually sift through the data and find insights there. Some organizations may have them using Tableau or Power BI or some other sort of visualization tool. But your data analysts are finding their insights and then telling a convincing story to decision makers to convey the underlying truth behind that data set. Now, AI engineer is a role that I believe Microsoft built, made up this name when they were making a certification test. You may find it under a different label, such as an ML engineer or something else. But think about an AI engineer as an application developer who happens to build a lot of applications involving artificial intelligence. So your AI engineers are building an application somebody can work with, but they are using machine learning models that other people have built, or potentially they built as well. So they have to understand the limitations of a machine learning model. They have to be able to communicate those to executives, project managers, and end users. And they have to be able to understand the reliability concerns that go with that. Okay? This one's really interesting to me, but you don't see a lot of roles for it out there. Data engineer, I jokingly call these the data plumbers of the world. They are making sure that data flows reliably and securely across a large organization that might have various data stores throughout that organization, various systems that need these. They're making sure that the data can be transferred at scale, reliably, and in a clean and secure process. So this is a programming role where you're working a lot with distributed processing, batch processing, extract, transform, load, extract, load, transform. These are all things that a data engineer is working with. So those are the big four that you're working with. Now, our wonderful folks over at Pathways and at Tech Elevator, which help our students with their career aspirations, helped me come up with some numbers, some salary numbers for data science roles in the Columbus market as of January of this year. And what you'll see from this is that most of these numbers are fairly comparable to those of software engineering roles. Right? Your data analysts are paid a little bit less, but on average, your data science roles are paid about the same as software engineers, though the senior levels tend to get paid a little bit more. Okay? I wouldn't let the salary aspect of things move you into data science or out of data science. If you find it interesting, more interesting than software engineering, go for it. Because the reality is by the time that you hit that senior level, these numbers are going to change. And they may be a little bit more equitable or more on par. So I wouldn't let this be your primary motivator, but it's important to know these numbers. And again, these things are going to be available online at matteland.dev/tryds. I also just put a tweet out there as well with links to that URL. Okay, so let's transition a little bit and talking about the data science workflow and what it looks like to do a data science experiment. So when you're training and deploying a machine learning model, you're going through a series of phases. You are acquiring some data. You are analyzing that data to make sure it's in a good state, it makes sense, maybe looking for some relationships in that data. And then you're going out there, you're cleaning up any oddities you find in that data. You're then training your machine learning model, making sure that model is unbiased, reliable, and fair. And then if you like that model, you're going to deploy it out into the real world where people can start to interact with it, use it in their applications, and get some value out of it. But your job doesn't end there. You have to keep monitoring it, as we'll talk about in a bit. Okay? So in a large organization, or most organizations, you already have some data in a relational database, in a data warehouse, in a data lake, data mart, something like that. You have data available to you. If you're just starting out, though, and you're just trying to do data science for fun, like I do, you're probably going to work with an API. Find somebody's free API or find a free data set, which is what I typically do. I go out to Kaggle.com, which is a free data science community that has a lot of projects out there and a lot of open source data sets. And I'm able to find interesting data sets and start building projects out of them. All these projects I've talked to you about before have been either via like the weather API or via data sets on Kaggle.com. So as you're starting to play with this stuff, I'd encourage you to go out to Kaggle. You can learn a lot. You can get a lot of data sets to play with. They do tend to be more clean than real world data sets that you'll find in the wild, which have bugs in them. You're going to have to do a little bit more cleaning with real world data sets. But it's good to get started. When you're doing exploratory data analysis, you are now visualizing your data. You're going out there and you are doing histograms and box plots, and you're doing statistical analysis and trying to find the distribution of these columns and looking for outliers. You're looking for missing values. You're looking for correlations on a scatter plot. You're trying to see what your data looks like. And if you find anomalies that are way out there in the data set, you may need to remove them. You may need to replace missing values. You may need to handle all these things. So the next step that we do is preparing our data. We do our data cleaning or data preparation or data munging, depending on who you're talking to. They're all roughly the same kind of concept. But you're getting your data into a point where we can send it to a machine learning model, right? So preparing our data, that's a really important part of our process. And it actually tends to be where people spend the most portion of their time in the data science process. They're preparing that data, making sure that data is in a usable state, right? You are also here, you're going to be calculating some columns that might help your machine learning models, and you might be removing some columns that might bias your data set as well. The next part's the fun one, the one that everybody thinks about. This is where we are training our machine learning models. With the machine learning model, the training process, this could look like writing Python code to use scikit-learn and trying to fit to a linear regression algorithm or whatever algorithm you want to try. That does require you to learn a lot of the different algorithms, and there are a lot of them out there, and they're scary, and that's where you start to get deep into the math. One of the things that I've personally found that's helped me on my journey as an early data scientist has been to use automated machine learning. There are libraries and tools out there that can help you, and what they do is they will try all sorts of different algorithms and see which one performs the best, and what hyperparameters to this machine learning algorithm work the best. And it's going to help you by understanding a little bit more about the mathematics of things and saying, hey Matt, I know you're trying to figure out if Die Hard is a Christmas movie or not. I really think that you want to be using this boosted decision tree over here, or this ensemble learning thing. Okay, I'll Google that later. Thanks, automated machine learning. So before you deploy something into a real world setting, you should understand it a little bit more. But using something like automated machine learning can help you out a lot. There's two ways I've worked with automated machine learning. The first way is through Azure Machine Learning Studio, which has ways of working with Python script, a drag and drop designer, or the automated machine learning or automated ML workflow, where you're going in and you're saying, hey, I want to do a classification task, here's my data, here's what I'm trying to predict, here's how I measure whether it's successful or not. Go out there and try to process this on 4 different computer clusters, or whatever it might be, right? So this can really help you a lot. And it tends to, if you're using like Azure's machine learning, it can be something like 17 cents an hour to run one of these clusters. It can actually be really affordable, especially on lower scales of data. Now, once you have a trained machine learning model, it's important to evaluate how effective that is. Let's say that I'm trying to train something to predict whether something is cancerous or benign. Well, sure, I went through the process and I fit a model and I have a model, but it's a 50-50 or 50% effectiveness. It's 50% accurate. Well, that's probably not a model I want to deploy for predicting whether or not somebody has cancer, because it's literally the same as a coin flip, right? So there's a lot of metrics out there that are associated with these different machine learning tasks. They tend to be about how accurate you are. Are you predicting things that should be true as true? Are you predicting things that should be false as false for a classification problem? For a regression problem, how off of the predicted value or the actual value was your prediction? If my windshield de-icer thing said, hey Matt, you're going to take, it's going to need 63 minutes to de-ice your car today, and it took 5 minutes, well, that's significant error. That's probably not a very good model. But there's a lot of these metrics out there. I'm going to be producing some content in the coming month or so going over the regression and classification metrics. So if you want to subscribe to me or follow me, I'll have more of that in detail, but we don't really have a lot of time to cover each of these in depth here today. Along with that, you need to be able to understand why your model is making the decisions that it's making. So let's say I trained a classification model to predict whether or not a loan would default. That's great. The accuracy is fantastic. But if I reject somebody's loan, or if I say, hey, I'm sorry, you're not covered for this on your insurance, or whatever it might be, they're going to ask me why. And I need to be able to give them a good, intelligent reason as to why I rejected their loan, or whatever it might be. So being able to explain why your model is making the decisions that it makes is a critical thing for you to be able to do. This is a screenshot from Azure Machine Learning Studio, where it's explaining the factors that are important to a machine learning model. I believe this is the Die Hard Christmas experiment that I did, one of the earlier models that I evaluated. So it's important to be able to say why your model is making the decisions that it's making, especially if they can impact people's real lives. Ethics. Ethics are a critical issue in machine learning. We need to be able to make sure that our models are reliable and fair and as free of bias as we can make them. I've been talking about this example of approving or rejecting a loan. Let's take a look at that and how I might have tried to build a machine learning model around that. I might have had historical information about whether somebody wanted a loan or not. It could have had information such as how much money they were requesting from my bank, the period of the loan, the location of their house as far as the city, state, and zip, their annual salary, their amount of time in their job, some other things like that. And I can run my machine learning model training process, and I can come up with a good and high-performing model. And I might think, this is great, this is amazing, it's almost always getting it right. I want to deploy it out there to the real world so people can take advantage of this. Well, there's a serious problem here because I may, if I followed that process I just described, I may have actually just released a machine learning model that is racially biased. I had no intention of that. The model had no awareness of race, but it is quite possible that I just did that. And the reason why is because, let's say that I have 1,000 records in my data set, and 4 of those records were of a certain zip code. And of those 4, all of those 4 people happen to default on their loan. It is entirely possible, and maybe even probable, that the machine learning model training process might say, hey, if I see this zip code, I should just always reject this loan, because that's what I've been trained to do. I didn't mean for it to do that, but that's what it learned from the data I gave it. So you need to be very, very careful about the data that you show your machine learning models. If it doesn't have any business being in your data set that you're using for training, don't include it. So zip code is something that has historically been a proxy for race, given racial segregation in America throughout the years, right? So that is how we could accidentally release a racially biased machine learning model that could significantly negatively impact people's lives. There are libraries out there like FairLearn that can help you detect and even compensate for this bias in age, gender, and ethnicities. So, but that's a whole different talk, and I've not explored that in depth yet. But this is a critically important thing for you to be considering in a machine learning model, especially if it could significantly impact someone. Okay? But let's say that you have a model that performs very well, you're happy with it, you understand how it's acting, and it's fair. Well, now you're ready to deploy it. The deployment process is going to be different depending on the technologies you used. If you're using Azure Machine Learning Studio, it's just a real simple click. You're like, hey, all right, I'm going to deploy a new Azure Container Instance or Azure Kubernetes Service, and it's just out there in production in 15 minutes, and people can work with it with a REST API. But if you're just making a model in Python, you might export that model as a pickle file, which is kind of like a serialized version of it, and then import it onto a Flask web server and build an API around it. Whatever it looks like for you, when you deploy that model, applications can now make calls out to it, or they're now incorporated into your application. But you need to keep monitoring them and making sure they continue to be fair and performant. For example, the used car sales thing. It predicts the price that a car might sell for. Well, that might be really accurate and really effective now, but in 5 months from now, when new car models come out, that's probably not going to be as accurate anymore. Or if there's suddenly a massive chip shortage or the chip shortage stops, well, that model is no longer accurate, and I need to replace it with something that's trained on more recent data. Okay? So all of this is really an iterative process where you need to continue to monitor and redeploy your machine learning models as needed, which is why you do need to worry about things like ML ops and repeatability and building repeatable pipelines for deploying and monitoring your machine learning models. Okay? So that's the workflow for data science. But there's a couple things I want to talk about before we move on. First of all, there's something called overfitting, and that's what happens when I say, hey, machine learning, I want you to just memorize all my data. What happens with that is if I give it all of my data, it learns the patterns in my training data, and it becomes really accurate at those things. But it's not as good at handling new things. It's not as good at seeing data, at making accurate predictions on things that it's never encountered before. So in order to avoid this inaccuracy at new data, which is really what we're trying to do, right? We're building a calculator to handle new predictions, not just historical predictions. In order to combat that, what we do is we split our data. We split it into typically an 80% goes to the training process and 20% gets held back. Sometimes it's 70-30, but something like that, where we're giving most of our data to the training process, but we're keeping back a little bit of it, and we're using that reserved data to evaluate the effectiveness of the trained model at predicting things on data it's never seen before. Remember, this 20% that we're keeping over, we know what we're trying to predict there. We can accurately measure our model's performance against it. This all seems a little weird and counterintuitive, but this is how we make sure that our model works well at predicting new values and not just memorizing the testing data. There's also something that we don't have time to get into, but it's called k-fold validation, where we partition our data into multiple different folds, and everything is used for testing and validation in turn, and it kind of averages it all together. It's more of an advanced concept, but it is an advanced form of this, and it helps make sure that your data is evaluated fairly and reliably. let's talk about the practicals here. Let's talk about what you're going to be doing as a data scientist when you're starting to work with machine learning and the things that you're building there. So I'm going to push pretty heavily towards Python. Python is a very good way of getting started with data science. It tends to be very easy for folks to learn, whether they know an existing programming language or if they're a business user getting into programming for the first time. Python is also increasingly being taught more in universities, so you're going to have newer students coming into your organization with knowledge of Python. There's a lot of libraries out there that work well with Python and machine learning, so it is what I would default you towards until you have an option to go with something else. Okay? But there's some other things to be aware of. R is a statistical programming language. It's really built more for an academic setting, but it has a very good data science community around it as well. It's really good for building. It's really good for building presentations and research papers and things like that. But I wouldn't get into it unless you have a really compelling reason to, because you're going to be able to do almost everything you could do in Python and have more support that way. Now, if Python and R are our reigning champions, then Julia is sort of the up-and-coming challenger. Julia is a relatively newer programming language that's built for parallel and mathematical operations. I expect to see Julia change significantly and get larger adoption over the next 5 years, but I think the learning curve might be maybe a little higher than Python or R for you. So I would learn Python first, and if you're really interested in Julia, start learning that after you've learned the basics of data science. But Julia is one to watch, and I suspect we'll be talking about it differently in a few years. So SQL. Raise your hand if you know SQL. Oh, good. I got the right conference. Yeah, so most of us know SQL. And we still need to be able to work with our data inside of the data science community. We need to be able to filter our data. We need to be able to aggregate, group, all that sort of stuff. Knowing SQL, even as a data analyst, is going to help you get the data that you need and make the decisions you need to. Additionally, if you are getting into things like Spark and distributed processing, there's flavors of SQL that can work on multiple parallel cores and can do a lot of distributed processing, distributed aggregating of your data. So your existing SQL knowledge is very valuable, and it's good to be aware of that. And finally, the other languages that you know, whether it's JavaScript or .NET or Java or Go or whatever, all these other languages tend to have machine learning libraries, at least one of them. I am a .NET guy. I've been using .NET since beta 2 back in 2001. And they have a library called ml.net, which is open source, and that's one example of it. TensorFlow.js is another one. These are all ways of using your existing knowledge and skills to perform data science experiments. But the drawback is that the communities of these things are smaller. The resources for learning these things are smaller. The capabilities are maybe not as good as Python or R and the libraries available there. But you can work with these libraries and do well with them. Another really cool thing that's somewhat newer is something called ONNX, or ONNX. That's Open Neural Network Exchange. With ONNX, we basically are able to take a model that we trained in one language and use it in a completely different one. For example, I could take a TensorFlow library or model that recognizes faces, and I can export it as an ONNX file, and then I can import it into ml.net and use it on an ASP.NET Core web server. And so I'm able to train a model in one language and deploy it in another. I think that's really interesting. That's another open source thing from Microsoft, which is, I love Microsoft. Sorry, I'm a fanboy. It's okay. But I'm going to assume that you're going to start with Python, because that's really the safest way of doing it. So let's talk about some of these libraries that you should be aware of with Python. When you're working with tabular data, such as data from a CSV file or a relational database, you're probably going to be starting to work with Pandas. And Pandas is a library that helps you sort of work with these objects called data frames and pivot and group and sort and filter your data. This is a really good way of playing with your data and getting a good understanding of it. Pandas uses a library called NumPy under the hood for numerical Python. And NumPy lets you, it's a very efficient way of working with data in parallel. So you can work with a lot of different rows at once. And Pandas just sort of does this under the hood, but you can also work directly with NumPy if you want to. Next, you often need to visualize your data. And Python gives us, honestly, probably too many options for visualizing our data right now. There's libraries like ggplot and matplotlib, which most people start with because they tend to be incorporated into Pandas. But then you have more advanced libraries like Seaborn and Plotly Express, which can help you build more advanced data visualizations. I swear by Plotly Express. It takes me about a line of code to make a really pretty interactive chart with tooltips and nice color and everything like that. And the documentation tends to be pretty good to get deeper into these things. So that's what I love, but whatever works well for you, do that thing. Whatever your organization does, do that thing. It's fine. But there's so many options out there for you. You should also be aware of Jupyter Notebooks. That's short for Julia, Python, and R. So Jupyter Notebooks lets you run a single kernel with one of those 3 languages and kind of mix it with Markdown. So I can have information about the data science experiment I'm doing or data analysis experiment I'm doing. Then I can have some code to load my data from a CSV. And then I can display some statistics to the user. And I can share this with my coworkers and they can say, oh, this is really cool. Well, what about this? What if I make this code change over here and I rerun the cell? It's kind of this iterative way of doing a data science experiment and mixing it with documentation. So it's a great way of sharing your data science projects as well. Big fan of Jupyter Notebooks. And you're likely going to want to do some machine learning in Python. There's a lot of different ways of doing that. The core ones that you're going to see the most are going to be scikit-learn, Keras, TensorFlow, and PyTorch. Now I have TensorFlow and PyTorch grayed out here for a reason, because they tend to be the more advanced machine learning frameworks. They give you a lot of power to do more advanced things, but you have to pay for that with the complexity that comes with them. You're starting out in an ocean of new things. You don't want to deal with complexity until you have to. So start with scikit-learn or Keras. I've done a lot of scikit-learn because Microsoft's examples have heavily featured it, and it's actually built pretty heavily into Azure Machine Learning Studio. But Keras is also wonderful. Now, Keras can do deep learning, while scikit-learn I don't believe can do that yet. I thought maybe they were working with it, but I'm not certain on that. So Keras is maybe more object-oriented, a little bit more verbose, but those are both good ways of getting started with machine learning in Python. An important note here is that Keras is really just a wrapper around TensorFlow. So you get some of the advantages of TensorFlow without having to have the additional complexity that you're going to bump into. Okay? So whatever you like, do that. It's okay. Go off and learn something. The concepts transfer pretty easily between these different libraries. This slide is maybe more for the data engineering roles, but when you are working with these things in the real world, you are not working with a small, 1 megabyte, 2 megabyte CSV file. You are working with an enterprise with tens of 20 or 30, 40, 50 years of data. And you have to worry about storing this data at scale and getting it out reliably and processing it reliably. So you're working with data lakes to store your raw unstructured data. You're working with data warehouses to store your structured data for analytical purposes. You are having to deal with extract, transfer, and load, extract, load, transform, and batch processing in order to deal with your data at scale. And additionally, your data is so big you can't fit it onto any one machine. It's just too big to fit into memory. And so you have to rely on distributed processing solutions, such as Hadoop, PySpark, Databricks, Snowflake, things like that. There's a lot of these names out there. It's very easy to feel imposter syndrome when you're getting into data science, is my experience. But baby steps, and you're going to be okay. Right? But there's a lot of stuff out there, and you need to be able to work with data at scale in larger organizations. So as we start to get through our close here, let's talk about some of the more advanced things that you can do eventually with data science and machine learning. And these are so awesome. I love these things. So there is anomaly detection, which is a form of unsupervised learning. We don't need to give it a training data set. It's going to look at your data and find anomalies. So this might be a credit card statement that our anomaly detection might flag for having an item that might look a little bit extraneous. But other examples might be looking at unusual network activity or an antivirus software that's looking for unusual program behavior. We're flagging things that look different so that we can isolate them or investigate them. That's what anomaly detection is all about. Okay? Recommendation engines. I think everybody here has used YouTube or Amazon or Netflix or even Twitter and LinkedIn and all these social networks. They all tend to use recommendation algorithms. And the idea of a recommendation algorithm is, if I like something and my coworker Rochelle likes something too, we both happen to like a couple of the same videos or ordered the same items, well, the system knows about the two of us. We don't necessarily know about each other. But it says, hey, Matt, Rochelle really liked this thing over here. You should check that out. And so that's what it's recommending to me. It's like, hey, users like you have liked this. And so you build a recommendation engine to drive engagement on your platform and keep people buying more, or watching more, or whatever you're trying to get them to do. So really powerful concept, maybe not so good on your credit card. Image classification. There's a lot of things you can do with images. Image classification is basically saying, hey, what is in this image? Now, last fall, when some of my wonderful students graduated, one of them baked a sugar cookie for me that happened to look like a pizza. Now, she did this because I teach arrays by opening Matt's Pizza Emporium, and I tend to be a little bit ridiculous as I teach to help it be memorable. And she's actually a pretty good baker, too, because this came out really well. But I took this image, and I showed it to Bing Visual Search. Bing had never encountered this image before. It's something I took with my own camera. And it said, hey, Matt, this looks like pizza. This is an image of a pizza. And I'm like, okay, well, that's cool. And then it showed me all these other pizzas that kind of look like it. So it was able to classify that image based on other images it's seen before. The thing I love about this slide here is that pizza in the upper right there, that's actually a cake. And it said, hey, this thing that I think is a pizza, it looks like this other thing that I also think is a pizza. Now, it didn't realize that they were both desserts, but it found some similarities based on the textures, I think in the white chocolate in both of them, that it was able to say, hey, these are similar to each other. So a deep learning algorithm is looking at the texture and color and shapes, and it's able to associate things. So kudos to my grad for tricking the Bing Visual Image Search. That was a good job there. So image classification is what's in my image. Now, object detection is looking at multiple things in my image. So this is my dog and I, we like to play hockey, especially in the winter. And an object detection algorithm might find all the balls, all the hockey balls in this image. And it's not saying just, hey, Matt, this is an image of some hockey balls. It's saying, Matt, there's a bunch of them, and here are their bounding boxes. So it's good at detecting what's in an image and where it is in an image. If I was trying to build a self-driving car, this would be really helpful if I could detect pedestrians or cars or traffic signs or road markers or things like that. Giving me a bounding box of something is going to be really helpful for me to avoid killing anyone with my self-driving car. So object detection is what's in my image and where is it. Now, semantic segmentation goes one level deeper. We're now looking at down to the pixel level. This is from Squid Game here, where we're looking at, hey, what meaning can I extract from individual pixels in this image? Oh, this pixel here is of a person. This pixel here is just sort of background. That gives you additional precision, which you could see being very helpful for a self-driving car of knowing exactly where something is in your image. So semantic segmentation is what does my pixel mean? Image classification is what's in my image, and then object detection is where are things in my image. So progressive levels of granularity. Facial analysis is another one that's a big one for us. So we can train a specialized model to recognize faces. So when I'm logging into my Surface here, I'm usually just looking at the screen and it says, oh, hey, Windows Hello knows who you are. It's memorized your face. That's a facial analysis algorithm that says, hey, I know you're Matt. I'm going to unlock for you. Another example of facial analysis might be saying, okay, this looks like a person, and our new APIs actually can tell from your facial structures maybe even emotions or what we think your emotions might be. So in here it might say scorn or anger or impatience or ridiculousness or whatever it might be. But we have the ability to look at facial structures and maybe start to infer some emotions, which is kind of cool because you can see that being helpful at maybe a storefront and saying, hey, this person might need a customer service attendant to help them out. But there's also some not so neat things that we can do with facial analysis. For example, these same APIs can also tell you what they think a person's gender is or what their ethnicity or age are. And that's not data that I'm quite comfortable with everybody in the world being able to get with a facial analysis algorithm. Right? There's some serious ethical implications of these things. You can also take a guess as to whether or not two people are related to each other. So these are some ethical concerns that we have with facial analysis. In fact, many cloud providers such as Microsoft are no longer giving police departments access to these algorithms. Of course, they can always roll their own, and I'm sure they have. But we have this policy now not to do that. Okay? So ethics remains a big deal in data science. Now, optical character recognition involves taking a look at some written or printed text in an image and extracting digital text from that image. So we can use this to digitize old receipts or newspaper clippings or whatever it might be. Now, text-to-speech and speech-to-text are all about, well, translating from one to the other. If you were building a digital assistant like she who shall not be named, who sits on my corner table at home and tells me what the weather outside is, being able to talk to that device, that relies on text-to-speech and speech-to-text. So speech-to-text helps her understand me, and text-to-speech helps the data coming back from Amazon's API be spoken aloud to confuse my dog, for example. But these are evolving technologies that really help us build more interactive applications. We can do a lot with text. We can translate from one language to another. We can summarize passages of text. We can extract key people, places, verbs from passages of text. We can even sorry about that. We can even look at text and get sentiment analysis to find out if a customer review is positive, negative, or neutral, or a tweet or a review of this session. And so we can start to get more and more information about the text that we're analyzing. So this is a really exciting field. This is a field some people just specialize in their whole careers. But we can do a lot with text. I love this one. Reinforcement learning gives computers a way of interacting with some sort of a simulation and a way of scoring themselves to see how well they did. You see this a lot with robotics and video games. You hear of games beating Go or Super Mario Brothers or whatever it might be. It's usually through this. They were using reinforcement learning to try something, get a score for how well it did, and adapt and evolve their approaches. One of the earliest machine learning things I ever did in my history involved a genetic algorithm where I was trying to evolve a squirrel that could find an acorn and get back to a tree. But it's a whole nother talk, and it's probably a weirder talk than this one. But talk to me later if you're curious. Now this one's weird. Generative AI. With generative AI, we're asking it to generate something for us. So in January, I said, hey, I want you to generate this picture of masked people at a programming conference. And it came up with this monstrosity, which still terrifies me. It was what I asked for technically, but it's not exactly what I was looking for. So image generation or image synthesis, taking together multiple images and composing a single one, that's an example of generative AI. You'll also see generative AI being used in generating sound effects and music for video games. You also see generative AI being used to generate box scores to generate articles in newspapers for different Little League games. So we can take a Little League box score and we can say, hey, here's a generated summary of that we can publish in our paper or maybe edit it. In fact, this last year we've seen Github Copilot come out that can actually start generating some code for us based on the code that we're trying to write that it thinks that we're trying to do. This is something that I think is going to significantly change over the next 5 years and significantly change our industry and many different industries as we start to see different machine learning models generate new things, which is both good and bad because it's change, and change is always interesting. So these are all things that you might be able to build later on in your data science journey. But Microsoft is awesome. Again, I'm a fanboy, sorry. But they give us this API out there called Azure Cognitive Services. We can go out and say, hey, I've got this text. Would you please generate a WAV file of a computer saying this in this particular voice? Or, hey, here's an image. What's in my image? Can you do some object detection for me? And we can use Microsoft's pre-trained APIs to use their models and get meaning for our applications. And you pay per use with those things. And there's a very generous free tier as well if you're at low capacity, which is good for if you're just doing hobbyist things or just prototyping an application. So Azure Cognitive Services is awesome. I want to get deeper into that over the next year or so. So let's say that you are convinced and you want to start trying data science. How do you do that? Well, it turns out I have some ideas, or I probably wouldn't be here, right? First thing you want to do is you want to start going to talks like this one. You want to start reading books. You want to start watching YouTube videos, reading articles, whatever helps you learn. Start doing that. And as you're doing that, talk to your friends, talk to your coworkers, tell them what you've been up to, talk to your boss. And like, hey, I went to Star Trek and I watched this really weird bald guy talk about squirrels. It was awkward, but data science is cool. And as you keep talking to people about that, they're going to say, oh, okay, well, yeah, you know a little bit about that thing. And you keep telling them about the things that you're trying for fun or for professional development, they're going to keep thinking about you, and the way that they think about you is going to change a little bit over time. So that's part of your journey. And once you feel that you have enough of a basic understanding of a small area, then you're going to want to start looking for some low risk or no risk opportunities to perform some experiments. I might say, hey boss, it's kind of quiet right now. We have this code freeze going on. I'd like to do some data analysis and see if I can find any trends in our usage data, or in the errors or tickets or whatever data source I have available to me. It's nothing where I'm going to deploy to production, but I'm going to start building these skills in a professional context and maybe sharing some value with other people. And once you have that, you start sharing the results with other people, and they can get value out of it too. And you just sort of repeat the cycle as you grow. Now, you might say, hey, I don't want to start doing machine learning in my job. I'm ready to just jump off, get away from software development, and become a data scientist or data analyst, data engineer, whatever it might be. Well, okay, that's a path. But you're going to need to be able to get a job in data science in order to do that. And that means that you're going to have to pass a data science interview. Now, full disclaimer here, I have never interviewed for a data science role. I am very happy teaching. It's the most fulfilling and challenging thing I've ever done, and I don't ever want to change what I'm doing. But if I was, I'd need to be able to answer interview questions about data science topics. I'd need to be able to tell people what I've already done. And I need to be able to convince somebody that my existing skills and knowledge are relevant to what they're doing right now and my future role. Okay? The best resource that I've found for getting started with a data science interview is this Ace the Data Science Interview book. It's a really, really good book. It's a little intimidating, but it's going to give you a lot of breadth into the types of things you might encounter in a data science interview, as far as statistics, programming, data, all that good stuff. So I recommend you give this a read and then learn some of the stuff out there. Just keep in mind, you don't have to be able to answer every question in an interview perfectly, right? But it's good to be able to know what people are talking about in an interview context. You also need to be able to have a portfolio of projects that you can share with people. At least talk about these projects, right? I happen to have a playlist on my YouTube channel that almost serves the same purpose of all the data science projects that I do. And they, again, tend to be fairly ridiculous. But if I was going to go off tomorrow and start interviewing, well, they tell me it's Saturday, I have to come back next week. But if I was going to go back next week and start interviewing, I'd talk through these decision-making processes that I've done with all my experiments. And they may or may not look at my code, but they're going to be able to get a sense of what I've done and what I might be able to do for their organization and the technologies I know and the ones I need to learn. So really important process is to start building something that you can talk about with other people. Something that can help you a little bit might be to pursue a professional certificate through Coursera or similar, or a certification through a formal body like I've taken several Azure certifications, and I'm studying for another 2. And this can help you a little bit as you're going on in your journey. But keep in mind that not everybody values certifications terribly deeply. So I would look at these more for formal skills development than convincing someone to hire you into their job. Okay? So as we close here, let's talk about how do we learn data science? What are the best ways you can do that? Well, I think the best way of learning anything is to go out and do it. Go out there and pick a machine learning task that interests you, whether it's classification, regression, clustering, or something else, and go out there and try to do it. The reason that I got in that argument with my wife about Die Hard, which Azure Machine Learning Studio helped me win, but the reason why I wanted to play with classification. I didn't terribly care about the argument, and it was a very fun project to play around with. So I found a project that was interesting, a task, then I found some data that supported that task, and I worked through the obstacles I found, and I got help when I needed it. And I shared the results with other people. Alternatively, I could have just started with a data set that I already had or I found interesting and found some machine learning tasks that worked well with that data set. I've done both of these approaches. They both work really well. The key thing is that I'm trying to build something, I'm building something that I can share, and I'm learning through the various pieces that I'm struggling through. Okay? So learn by doing. That's my best advice. And you're going to feel overwhelmed with all these technologies and libraries and algorithms and statistics and math and all that good stuff. Look at it as baby steps. It's just a skill tree. You're learning 1 or 2 things, and your next project, you reinforce that, and you add another thing to your list of things that you've been able to do, right? And you just build over time. I've been focused very intently on data science for the last 8 months or so, and this is the process I've been going through. I still feel imposter syndrome sometimes, but I'm learning, and I'm consistently getting better, and that's what you have to be able to measure yourself at in anything, but in particular, programming and data science. One of the questions that I am asked frequently as a software engineering instructor is, Matt, can I really write programming code? I don't understand trigonometry very much. I'm like, yes, you don't have to know what a cosine is in order to write a for loop. It's okay, you can do this, right? The same concept is somewhat true in data science. Data science is often related to statistics, calculus, and linear algebra. I personally do not feel that you need to understand a lot of the depths of linear algebra and calculus in order to do any sort of data science work, because there's a lot of things that can abstract this stuff away from you. Now, as you get deeper into these things, as you start deploying machine learning models, it's good to dig deeper into the technicalities of what you're investigating, but you don't need to have this starting out. Statistics, however, is one that you do need to expand your knowledge in as you're just getting started, because it's going to help you understand the data that you're working with. It's going to help you understand the probabilities you're working with, the distributions, anomalies in your data, missing data values, things like that. You don't have to know statistics to start with data science, but it is important to start refreshing and expanding your knowledge of statistics as you're getting started. So as you're getting into data science, refresh yourself, expand your statistical knowledge, and then take it from there. But you don't need to be a statistics master to get started on day one. Finally, go out to Kaggle.com, do a classification experiment. They have a classification experiment that's very classic to do of the Titanic and predicting whether or not a passenger would have lived or died based on their ticket information. This is weird, but data science apparently are very morbid. But you can go out there and walk through this project and learn a lot about data science by looking at how other people have solved this problem and find other data sets to work with. I've benefited a lot from Coursera and specializations and doing project-based learning. This is a paid kind of thing, though I believe you can audit these classes as well. But these 3 specializations, the Python 3 Applied Data Science specialization and Microsoft Azure AI Fundamentals, have all significantly helped me in my own skills development. And there's also resources on YouTube. If you enjoyed this talk and enjoy my flavor of nerdery, give me a subscribe. It actually helps encourage me as I spend my nights doing weird things. But there's plenty of other channels out there as well if those are more your cup of tea, right? And if you are interested in ML.NET or machine learning on the .NET platform, I have a pre-recorded talk going out tomorrow for Sci-Fi DevConf on determining what makes a good Doctor Who episode versus a bad one. So check that out, and I'll tweet that out on Twitter as well. Again, my resources are all at this link at matteeland.dev/tryds. And if you build something awesome, please tell me, because I really love seeing you all getting engaged about the things that I care about. And finally, just thank you, Star Trek. This has actually been a bucket list item to speaking here in person, and it's been an honor to speak. So thank you all, and thank you for spending your time with me.